Logarithmic functions. Notice we have exponential functions mentioned here, and we have logarithmic functions over here. The reason we put them together is that they're related. They're inverses of each other. Inverses has this feeling of like reverse. Notice the point AB on the exponential function graph becomes the point BA on the logarithmic function graph. Notice that the domain of the exponential looks like the range of the logarithmic, and the range of the exponential looks like the range of the logarithmic. So they switched everything around. Notice the asymptote is horizontal for the exponential, but it's vertical for the logarithmic. These are some names of locations. If you put a number in exponential form, it would be 2 to the third equals 8. This number is called the base, the top one is the exponent, and the one over here by itself is just called the number. The logarithmic form, you put an log and you put the base down here, the number up here, and the exponent all by itself. So now we could transfer from one form to another. This side is exponential form, this side is logarithmic. So how would you write 2 to the third equals 8 using logs? You would put the log. Notice it says the base goes here. So this is the base, it goes here. This is the one that's called the number, it goes here. And it equals the exponent, so the exponent goes by itself. So we went from exponential to logarithmic form. Now we should be able to go from logarithmic to exponential. This is the easier one. Just draw a little arrow from the 10 to the 2 to the 100, and then just say 10 to the second equals 100. Just follow this arrow. So this logarithmic form has turned into this exponential form. In your calculator, you have two keys. One is called log and the other one ln. The log key, your calculator is going to understand that it's a base 10. This one's called a common logarithm, a base 10, log. If you use this key, ln, your calculator is going to understand that you're using base e. This was called the natural logarithm. How do you convert from 1 to base 10 or base e? So notice this is base 5. Your calculator, if you were to key it in, wouldn't understand that. So we have to change it to the form the calculator understands. All you have to do is give each of these numbers its logs. So notice, log of 7 base 5. You give the 7 the log, and you give the 5 a log. Key this in, or you could key this in. You could give them both an ln. You get the same number either way. Take your pick. These are properties of logarithms. They allow you to change from one form to another. Sometimes it's convenient when you're simplifying or solving equations that involve logs. Right here in the first property, we see that the log of a multiplication is the same thing as the sum, the addition of the two logs. So addition and multiplication are associated when you're talking about logarithms. Right here we have a division. So a division is associated with a subtraction. So the log of a quotient is associated with the difference of the logs. This one allows you to move this number up here. Notice these two are equal, but the number on this side, the r, is down here, being multiplied times the log. And on this side, the x is being raised to that r. You could put it up here or down here, whichever one's convenient for the problem you're working. Write each as a single logarithm. So we have two logs, but we're going to use the property to condense them to one log. The first thing we notice is that this is an addition, and addition is associated with multiplication. So what you do is you write one log and then multiply these two. Here they are. Don't change the base. This one is giving us a subtraction of two logarithms. A subtraction of two logarithms is associated with a division. The first one you came across goes in the top. This second one that you came across goes in the bottom. So you've condensed two logs that were being subtracted to one log where the arguments, either called the arguments, are being divided. This one, you're going to move this 5 up here. So that's what we did. Notice that property, the third property we talked about, allows you to move this 5 up here as a power. This one, we just copied it. Then you look at this and you see this in addition, so you go even further. The addition is associated with multiplication, so it's 9 times whatever is here. And you just write the log once. Keep the base. Here's another example. This radical, its number is 1/2, a power of 1/2. So when you take the square root of a number, you're really raising it to the 1/2. So once you have it up there, notice what they want us to do, expand it. In this case, we're going to expand. So you use that power rule, the third property, and you bring the 2 down. Here it is. The rest is the same. Then you notice these are multiplications, so you're going to turn them into additions. So it's the ln of 6 plus the ln of n to the 4th plus the ln of n to the 2nd. Then you look at this, and you could bring this power down by using the third rule of log. So this 4 goes down. This 2 goes down. Now distribute the 1/2. Simplify. So 1/2 ln of 6, and then 4 divided by 2 is 2. So this would be 2 ln of m. 2 divided by 2, 1. So this one turns out to be ln of n. Ln of n. Now we're going to solve using exponential logarithm equations. So what you're going to do, ultimately, you need the x to be in one place all by itself. So this is all spread out. So that reminds you that you have property of logs that allow you to condense it. So these two can be condensed. It is a subtraction of logs. You could turn it into the log of a quotient. So the first one goes on the top, the second one goes in the bottom, and the subtraction turns into a division. Notice how it's shrinking. At this point, notice that they're telling us that these are equal. So what you're going to do is match them up. Log equals log. Base 10 equals base 10. So this should equal this. We call it a 1-to-1 correspondence. So now, since you've matched them up, you don't have to put the log. Now you continue with this equation. You cross multiply. This one times this is this one. This one times this is this one. Distribute. That's this left side. This one's following along. Then move everything to the left side. When you have x to the second, x to the first, move everything to the same side. Once you have them all on the same side, this is a quadratic. The next step is to factor. So you factor this one. This is what it factors into. So something times something equals 0. So either this something is a 0 or this something is a 0. How can this be a 0? Well, if the x was a -1. How can this be a 0? Well, if the x was a +3. Now, this next step is very important. If your equation were logarithms, you have to check the answer. So even though you're sure of all your algebra, when you're working with logarithmic equations, you have to check them. And what is it that you check? What is it that you're looking for? Well, if you remember, a log, the domain of the log only allows positive numbers here. This can be a positive number, this can only be a positive number, this can only be a positive number. So if you were to replace the x with a -1, that would give you a negative number, but LOGs do not accept negative numbers here. So this x equal -1 is disqualified. If you check x equal 3, that one doesn't cause any problems. So the only solution is x equal 3. Now they're asking us to solve another logarithmic equation. This one, notice you have log, you have the log of 2x minus 3 base 5 equals 2. So this one, you could remember, you could change this form to exponential. Remember that little arrow we said you draw here? So you could rewrite this 5 to the second equals 2x minus 3. After you rewrite it, you don't have to write the log. Now it just turns into a regular equation. 5 to the second is 25. Get the x by itself, follow those steps, combine like terms. Finally, you divide both sides by a 2, and you have x equaling 14. But since this was a logarithm equation, you always have to check your answer, put it back in here. 2 times 14 minus 3 gives you a positive number, so the log is going to be okay. If I would have plugged it in and gotten a negative number, then I would have to have thrown that answer out. Here's another solving. This time, we don't have logarithmic equations. These are exponential equations. How do you bring a variable from the power position down? You provide a log. Anytime you want to bring a variable down to the base level, just take the log of both sides. And then by using that third property that we mentioned some time back, you could bring this x down. Now that you have it down here, just move everything away from it, which means divide both sides by the log of 9. So you divide this side by the log of 9, divide this side by the log of 9, this cancels to 1, and x is going to be whatever you get from here when you key it in. So I key it in to the calculator, and it gives me this. So x equals 1.5. Here we're going to solve another exponential equation. Notice that the variables are up in the power position. The way you bring variables down to the base position is by taking the log. So you take the log of both sides. If you take the log of one side, you have to take it of the other side. This allows these powers to come down to the lower level, to the base level. Now we distribute here, and this is what we have. Distribute on this side, and this is what it gives you. Now collect all the terms that have x's. So I'm going to bring this one over by subtracting it, right? And I'm going to take this one over to the other side by adding. So I'm collecting all the terms that have x's and all the ones that do not have x's. Now that I have these two terms, I could factor out an x so I could have it in one place, not spread out, but in one place. Now this allows me to divide by this. So I divide both sides by this portion so I could have the x by itself. So this is going to come underneath this one. This one's coming down over here, since this was going to also be divided by this quantity. So you do the division and carefully key this into your calculator, and you get approximately a solution of x is approximately 4.774.